Something that's often really helpful to do, something that we have to do all the time in pretty much every field of math, is to compute the sum of a bunch of elements of a sequence. This can happen, for example, if you want to figure out the runtime of a program and you can break it down into a sequence of runtimes for individual subtasks. It comes up when we're doing tasks in mathematics, totals of things, integration of functions. Lots of reasons why we need to be able to compute sums of stuff. So if we have a special notation for this, our notation uses this funny squiggle here. This is the Greek capital letter sigma. It makes an S sound, and it's just a fancy S for the word sum. So when we want to compute the sum of a bunch of elements in a sequence, we use a sigma here, and we call this sigma notation. When we use sigma notation, we need to specify what we call the index of summation. So I'll write that here. So this is the index of summation. And with this index, we have a lower bound. In this case, the example I've given, the lower bound is 0, and an upper bound, which is often a variable that here I'll call n. And then to the right of the sigma sign, we write a sequence, or sometimes we write a formula for the sequence as well. And we just write a single element of that sequence with the index corresponding to the index of summation. When we write this, we pronounce this as the sum from I equals 0 to n of the sequence a sub I. And what this means is that I'm going to take everything from the smallest value of I equals 0, to the largest value of I equals n, and everything in between, and I'm going to add them all up together. So here's a few examples of this in action. Let's consider first the sum from I equals 0 up to 4 of the sequence with the formula 2 times I. So what I have to do here to evaluate the sum is I plug in all the values of I possible between 0 and 4 inclusive. So that means I'm going to get 0 is the first one, and then I equals 1 is going to give me 2. Then I equals 2 is going to give me 4, I equals 3 is going to give me 6, I equals 4 is going to give me 8, and then I'm done because I've reached the upper limit of the index of summation. And so my result here for this sum is 20. Another example, let's consider the sum from I equals 17 to 20 of the expression I plus 1. This is the sequence I plus 1. And what I've done here is I've chosen a pretty unusual lower bound on the index. That's allowed. You can sum with any lower bound you want as well as any upper bound. That's all allowed. So here, I need to plug in I equals 17. I get 18 when I add 1 to it. Similarly, I'm going to get 19 when I plug in I equals 18, 20 when I plug in I equals 19, and 21, and then I am done. And this is equal to, here I'll show you an arithmetic trick. I'm actually going to add together the 18 and the 21 first. So if I add the 18 and the 21 first, I'm going to get 39. And then I'm going to add the 19 and the 20 first. So if I proceed inside that way, I'm actually going to get 2 copies of 39. And that's a little easier for me to work with. I get 78. One more example. An easy mistake to make is if my index of summation actually doesn't appear inside my summation sign. So here, I'm just going to write an x here, where x is some other variable. Notice that what happens here, this doesn't have I in it in any way. I is not involved. And that means that I'm just going to add up 1 copy of x for each of the possible values of I. I have a copy of x for I equals 0, a copy of x for I equals 1, and a copy of x for I equals 2. And so my result is 3x, 3 times x, because I didn't have anything that depended on I inside my summation. We can be pretty flexible about this notation too. For example, there is nothing special about the letter I. I could also, if I wanted to, nothing wrong with having the sum from k equals 0 to n of k squared, for example. Now that's my index of summation k, and I'm going to consider all the possible values it can take between 0 and n. Nothing special. I can change the letters however I want, as long as I'm being careful about not reusing them for different things. It's a little less common, but also very helpful to compute products of the elements of sequences, products. So a product is just like a sum, except instead of addition, we're doing multiplication, and we're going to write it just a little bit differently. So here's our notation. In order to compute the product of the elements of a sequence a sub I from I equals 0 all the way up to n, I am going to write this big funny symbol here. This is a capital Greek letter pi. So just like the pi that's in all the formulas for circles that you learned about previously, this is the capital version of that, and it's P for product, just written as a Greek letter pi. So in order to compute a product, I write this big letter pi, and then the rest is very much like sigma notation. I need a lower bound on my index, I need an upper bound on my index, and then an expression inside the product. And the result of this is going to be that I simply multiply all the elements of the sequence together from A0 up to AN inclusive. So here's an example, and here's we're going to start with an easy mistake to make with products. So suppose I consider the product from I equals 0 up to n of just the sequence I itself. Okay, what is this going to give me? I have to multiply 0 times 1 times 2, and then I'm going to multiply a bunch of other things, and eventually I'm going to get to n minus 1 and n as the final elements of my product here. And guess what? I have multiplied by 0, so my result is 0 no matter what n was. So not very interesting. This is a sign here. Be careful when you're doing products with the indices. They can make a really big difference. On the other hand, if I just adjust my index a little bit, I equals 1 up to n, and consider the same task. This time I get 1 times 2 times a bunch of stuff all the way up to n minus 1 up to n. And this is a product, there's no formula for it really, but it's such an important product that it has a name. It's by definition written n exclamation point, and it is called, or pronounced n factorial. This is the factorial function, n factorial. I do all the integers, or all the natural numbers, excluding 0, up to n, and I multiply them together. So I can define this factorial operation in terms of products. This is a very important operation that will come up again when we get to counting problems and combinatorics soon.